Insiders and Germans particularly know, of course, Fraunhofer, but perhaps you could tell us a bit about Fraunhofer itself and then your institute and what you people do there.
So we are the largest, Fraunhofer is the largest research organization for applied research in Europe, with more than 72 institutes and 26,000 people working. So I'm head of the division of one of these institutes, and we work on application of microtechnology for two main areas. The one is energy and chemistry, and the other one is analytical systems and sensors. And today we will talk mostly about the energy part, and that is making, among other things, making hydrogen for fuel cells.
Public attention has been attracted to fuel technology for various reasons. People emphasize, for instance, we're curtailing renewable resources, we're shutting down wind turbines, and the options available are to turn electrical power into something else. So there's a lot of power to X. What can you do with electrical energy if you turn it into hydrogen, for example? So when you think of power to X, what are the options available, and what are the options that really interest you in working with electrical energy and its potential through hydrogen?
So first step, of course, most obvious is taking water and make electrolysis with it, get hydrogen out. And then you can take that hydrogen, as you know, and convert it CO2, carbon dioxide, from the atmosphere or from the large industry like cement industry or steel industry, and convert that to natural gas. But this is something for the future and which must be driven by politics a lot. If you look at commercial viability nowadays, it might be more wise to make chemicals of much higher price, because something like methane or even synthetic diesel is something which can be bought on the market still for a very low price, and you could make other chemicals which are maybe 10 or 50 times higher in price and use the electricity and maybe the hydrogen to synthesize them. So they are alternatives and they should be considered.
So the options are manifold, but the business model is not always clear. One can go the other way. We have this immense supply, of course not in Germany. Germany is entirely dependent on imported hydrocarbons, for example, natural gas. But we have this high-octane, relatively clean source of natural gas. You can reform that and use that as a source of hydrogen. Why would anyone want to do that, though? What would be the point of reforming natural gas, involving a loss of energy, maybe insignificant, and then doing something with the hydrogen? Is there a reason to do that?
And this is what is done by chemical industry. Nowadays, of course, the huge reformers, they need the hydrogen for different application, and this is what is currently still economically viable. And then we want to use the gas grid which is existing and get a better efficiency. So what we normally do is we combust the hydrogen, but if you look at Japan, there are 300,000 fuel cell systems running, and they are running with reformers, with fuel processors, transferring the natural gas first to hydrogen and then to electric energy. Why? Because the efficiency is very high of the process. You get a lot of, compared to combustion engines, you can get better efficiency electricity-wise, and you can, of course, also use the waste heat of the process additionally to generate for heating purposes.
We've seen these devices before. In our prep talk, I was mentioning they've kind of disappeared from the displays here, but 10 years ago you could see what was really a small, very convenient unit. You could install it into a home or an apartment, like our typical Gas-Etagenheizung. And interesting, it provides heat because the PEM cells do produce heat, but the other factor is it supplies electrical energy. And that electrical energy would even be cheaper per kilowatt hour than what we buy over the grid. So why isn't this taking off in Germany? What's inhibiting the implementation of something that is 30% more effective in terms of using natural gas. Do you have any idea why that's not caught on here?
It's developing. The number of prototypes and the number of systems which are running in the households is increasing. We are just a little bit behind Japan, who started all that development earlier. But it's developing also.
So Japan got their foot in the door earlier, but we're catching up.
Yes.
Okay. What's new this year, and the pictures are phenomenal. It's too large to drag up onto the stage, of course. It's the 50 kilowatt natural gas reformer for hydrogen fuel cells. Could you describe that system? It's a large device. How large, and where is it going to be built, and what exactly does it do?
So we use it as a demonstration plant to show our technology. We can make very compact reactors with our technology. I brought one of them with me. So these are plate heat exchanger reactors. For this 50 kilowatt system, certainly a little bit larger. But we get very good heat integration in the reactors. We have here a plate heat exchanger, which is coated with catalyst. And then we can remove the heat easily or supply heat to the chemical reaction, depending on the demand of the system. Yeah? So the system will be operated, complete fuel processor, also with sulfur removal and carbon monoxide removal, which is necessary for natural gas. This will be operated together with a low temperature PEM fuel cell, which is from PowerCell in Sweden, and we'll use that for, as I said, for demonstration purposes. It can be much more compact compared to conventional technology. And that is important for some specific stationary applications, but even more for mobile applications. So thinking of all kind of applications, can be surface transport, can be maritime, can be even in the aerospace sector.
The interesting thing from my perspective, the more you look into this technology, the more you have really a large selection of options in terms of operating temperatures for devices, size, of course, and scalability, whether you need lightweight or you want a stationary application where the weight doesn't matter. The 50 kilowatt natural gas reformer that you've developed has an operating temperature of 800 degrees.
The reformer itself, which is the core part, the other components are lower on temperature, and the fuel mostly determines the temperature of the reforming process, of course. So you need quite high temperature, for example, for natural gas. You need it also for diesel. For alcohol fuels, it's much lower. For methanol, it can be in the range of below 400 degrees. Yeah? What we call already low temperature.
Okay. Sounds hot to me. But for higher operating temperatures, is there, if you're really working towards, and most engineers think about overall system efficiency, if you're thinking about efficiencies, does it make sense to try and recover the heat generated and apply that, or is it simply accepted as the operating temperature?
Yeah, but the operating temperature does not determine that. I mean, the question is, how efficient do you want to generate your system? And that determines the number of heat exchangers and the number of heat recovery devices you have inside. So this is one thing. The other thing is the operating temperature. And there you need a better insulation, as simple as that. Yeah? You have to take better insulation materials which reflect the radiation, which is very high at 800 degrees, and then this is also fine. Yeah. So these are two things you have to.
Okay, they separate them. Is there any? If we think of the case of grid stabilization and other factors, some people think that quick startup can be a desideratum, something you really want to have. Is that something that is at all of importance for this device, whether it starts in 5 minutes, 10 minutes, 45 seconds?
That depends a lot on the application.
Okay.
Yeah? And then you can use different strategies to achieve that. And generally, a reformed fuel cell system cannot start from cold, from completely shut down to operating within less than, let's say, 5 to 10 minutes. So this is the minimum time demand you need. So in case you have a mobile system, it might be necessary to have some battery in between to buffer that. But it depends really a lot on the application and when.
Interestingly, we started with this large-scale stationary application. We discussed also the possibilities of reforming in-house in apartments and using that as a decentralized grid for both heat and electrical power. We haven't discussed mobile applications, which is sort of the focus of the consumer attention and also the media attention. People know that you can have a fuel cell car with a tank in it, pressurized hydrogen. Some people are doing different things. You're a reformer specialist. What are the options if you want to have either a range extender in an electric car or a fuel cell car powered by a hydrocarbon, which you don't need to pressurize? What are the good options out there, and how much sense does it make to use a reformer in a mobile application?
So, very clearly, the combination of a smaller scale battery with a reformer doesn't need to be at full size of the engine, of the drivetrain, is a very good option. And using a liquid fuel which has a much higher power density compared to compressed hydrogen is, I think, on the long term, maybe something which might stand on the market. Yeah?
Okay. We all know that pressurized hydrogen is, contrary to popular belief, safe in cars. There's a lot of people who do testing. If you're in the airline industry and you're trying to supply power, you might not want to have an extra 700 bar pressurized hydrogen tank, but you may also not want to have methanol or some form of diesel fuel within the cabin to power all of the electrical devices that you now have on a plane. Do you have any solutions to that, something that is safe and nevertheless an energy-dense source of hydrocarbons for a fuel cell?
Yeah, so this is what we are developing together with our partner, the Aerospace, for quite some years. It's an energy trolley which can be operated in the passenger cabin of the plane. The fuel we are using is not flammable. You can drink it. You can eat it without any limitation. It's propylene glycol. And it's not easy to reform in combination with water. As I said, it's not flammable. And we decided to go for that fuel, especially also because it's used as a cooling agent already in the aircraft. So there's already a certificate for using in the aircraft industry. Yeah? And it's also used for de-icing purposes. Yeah? So, an alternative for a very specific application. And we have developed the first fuel processor for that fuel worldwide. And we are building now a second generation prototype of that.
These are, for me, the fascinating success stories because basically we're all interested in getting the volume of fuel cells marketed year by year up. And the niche markets are the ones that are really operating well, the forklift trucks in logistics that work indoors, that it's the best option, the fuel cell and battery combination here. But it's so interesting to hear a news story. You need a source of hydrocarbons that is available. We don't have a hydrogen grid anyway, but using materials that are available at the airport that are already certified to carry on board, and you can drink a glass of them and it's not going to kill you.
If you look at that, yeah, you can imagine that you start that up already on ground. Yeah, the plane comes down. You take the other one, the other trolley out, which the tank is empty. Yeah, the people are filling that on ground, and they put the new one, which is in standby, in. Yeah, so there you don't have a problem with startup time. This is what I meant. It really depends on the application. Yeah, and there you have well-trained personnel which know what they are doing. Yeah, so it's a completely different environment compared to a passenger car, of course.
And of course, the positive side is the issue is weight there, I suppose, and the number of batteries you would have to supply the same amount of energy.
You always end up, when you calculate, you end up very easily with the result that a battery has a too low power density. Yeah? So if you look at such kind of applications, yeah, so certainly.
So we've gone a relatively large loop. I'd like to bring it back to the combination of reformer technology and fuel cells and mobile applications. The reason is there seems to be already a market. The niche markets are already established. The forklift trucks, they do have batteries as well. Well, all fuel cells have batteries, but small batteries, and they're self-charging. Batteries don't like to be depleted 100%. They don't like to be overcharged. They don't like to be fast charged. So the fuel cell and the battery combination is this perfect marriage. But the problem, if we are purists, is if you want to operate that with pure hydrogen, where's the hydrogen network? So we need other sources of hydrocarbons right now.
As we said, we have the natural gas grid here in Germany as one example. Yeah?
The natural gas grid is one. Okay, so are there mobile applications for pressurized natural gas and fuel cells that you know of? We're talking.
No.
Yeah. Okay. What about methanol?
So there's a grid existing in China, for example, and methanol, as I said, is relatively easy to reform. So that is an interesting application also for mobile vehicles, for vehicles. Yeah.
And it helps a lot, of course, that there's a methanol grid in China, which is sort of this pre-existing advantage. When you look back with 20 years of experience and you see the status of the market right now, you know the material sciences involved. Some of the issues are very straightforward. Can we cut down the cost of the fuel cell by removing precious metals? What about the fate of the catalyst? Do they deteriorate? Is there a lifespan there that makes it an affordable device that operates for 10 years or however long you're going? That is, you look at the material sciences, and all of the developments also influence application perspectives and the financial viability. If you look into your scientific crystal ball, where do you see potential developments? Where do you see good commercial prospects or energy efficiencies that we should be aware of?
So I think for the fuel cell itself, it will be still a challenge, but there are developments on their way which will make it possible to decrease the cost of the catalyst, the electrocatalysts, yeah, so something different to a reforming catalyst. And the same applies for the reformers, but it's not so critical in that case here. And that is as simple as you can think of. You have much higher operating temperatures in the fuel processors, in the reformers, and that already makes the activity of the catalyst very high. So here it's more the manufacturing technology to make the reactors cheaper as a major step forward in the next future. Yeah? So you need compact reactors and you need to make them cheaply. Yeah? And I think this is what will bring us forward here.
Okay. Well, it's always a pleasure to talk to someone who's working with 20 years of experience in developing reactors and systems for hydrogen technology. Professor Dr. Gunther Kolb, Head of Division of Energy and Chemical Technology at Fraunhofer-Institut for Mikrotechnology and Microsystems. I hope to see you back here next year to see what developments you've come up with. Drinkable hydrocarbons, non-toxic, and you don't even get hammered, right? See you back here next year. Thank you very much.